Happy to welcome our first speaker today, Professor Markus Püschel. So it's my pleasure to welcome Markus. Markus is a professor here in the department. He's been here with PTH as a full professor for the last 6 years. Prior to that, he was a professor at Carnegie Mellon University. Markus is very well known for his work on essentially program synthesis for performance, right? So taking high-level mathematical descriptions, very important mathematics, and then making it super fast. So he's particularly also very famous for the spiral system, well-known system for building generators for linear transforms. So that's a system that is known, and that many of these techniques have been actually commercialized later. So today he'll tell us a little bit about this direction. So please go ahead.
Okay, good morning, everybody, and particular to the visitors from the US, respect for getting up at this time. Yeah, thanks for the kind introduction. I don't know about the famous, but you know, like everybody, we're trying to do good work. So today I'm talking about exactly the topic Martin has mentioned, program generation for performance, particular domain linear algebra. And this is the work of my PhD student Daniele Spampinato, whom you see here. So if you like the work, all the credit goes to him. You may wonder, why is he smiling so much? I mean, he's a very cheerful person, but maybe he smiles a bit more than usual because he will soon graduate. Okay, and move on to the next step. Good. So here is some mathematical computation. Does anybody know what that is? The Kalman filter, exactly. This is a Kalman filter, and it's one of the blockbuster mathematical algorithms, meaning one of the algorithms that is used all over the place in control. As a little side comment, Kalman was also here at ETH for 20 years, had a professorship, right, from the 70s. And I just checked this morning on Wikipedia the stats. He just died actually 2 months ago, 8 weeks. Anyway, so the Kalman filter is used in many applications, for example, in robotics, right? It can be used to control robots. You see it's a couple of computations involving matrices and vectors. There's an inversion, and to compute this, you need a Cholesky factorization, so it's linear algebra stuff. And the size of these objects is given by the number of states that you control, like velocities, position, and many other things. Could we have 13 states? Okay, 13 states, meaning the matrices here are of size 13 by 13. Now this is very relevant, and not just to have a correct implementation, but you need actually a fast implementation, because you want to do it in real time, right? A robot should move at some decent pace. The faster it is, the more things you can do at the same time in real time. And if the robot runs on a battery, and actually you do this on board, then the faster it is, the more efficient it will be. It will drain your battery slower. Okay, so speed really matters. And this applies actually to many domains of mathematical computations. So let's assume there's this engineer working in robotics, let's say over here in our robotics group in the other department, and wants to implement this Kalman filter, and it has to be fast. So what does the person do? So one option is you can go out, you try to find code, or you find a library. That has its problems. I will talk about libraries later, but you know, it's easy enough. You think I can just do it myself. Person sits down, is a good programmer, writes some C program. Now, I don't have a C program for this computation, but I have a few other C programs that were created like this, and I show them here. So what you see here is 3 other sort of blockbuster functions. There's matrix multiplication, which occurs in the Kalman filter, Fourier transform, and here's a Wi-Fi receiver, which in essence is a Viterbi decoder. Okay, these are all mathematical functions that need to run very, very fast. So what you see is these are performance plots. On the x-axis is always the input size, right? So input from small to large. And on the y-axis, I show performance in giga floating point operations per second, or in this case, actually integer operations. That's even a mistake. So higher is better. It's like inverse runtime. So I show in each plot 2 lines. Here is straightforward C code, meaning some talented normal programmer sits down and writes a decent C or C++ program, compiles it with the best compiler, like let's say This was done on some Intel processor with the Intel compiler, all the optimization flags, and you get the performance of these gray lines. You may think this is just fine if you don't know that there are other lines out there like these red lines. And these red lines is code that was actually highly optimized by some of these guru people who can do these things, right? They kind of do weird things to the code to make it really fast. And the difference here is, here's about 100x, here it's 30x, and here also is a 30. And this is a processor with 4 cores, and this code is not even parallelized. Good, so in all cases, from here to here is the same operations count, so we didn't get rid of any math. The ops are the same, best compiler and optimization flags. Okay. If you see this the first time, something like this, you may think, oh my God, how is this possible, right? Same op count, good compiler, how can I lose a 10x or a 30x? So to understand the reason a bit, here I show what happened to computers in the last 2 decades or so. So here on the x-axis you see years, and here I show Intel processors. You know, back in the days there was something called Pentium, and there were various iterations, and we have these processors. So this plot shows CPU frequency. It's a log scale, so you see CPU frequency increased a lot. Software got automatically faster. Everything was great until something happened here and it has gone flat. So these times of the super easy free speedups are over. And I guess many of you have seen plots like this. So this is an inflection point, really important. Something has really changed. Free speedup over. That's the bad news. The good news is the peak performance of these platforms, how many flops they can execute per cycle, that has gone up. And of course, the only way you can do this is by parallelism. You put more units, vector instructions, you put more cores. But to get this performance, you need to put in work. It just doesn't happen by itself. Okay, and what's also maybe interesting, this parallelism, you think of multi-core, but actually it's equally divided between increasing the number of cores and increasing the length of vector units, right? So vector instruction now can do 8 ops at the same time. You have 8 cores, so you see it's evenly distributed, the parallelism. It's not just multi-core. Good, and then there's another thing, bandwidth, right? Bandwidth also goes up at some exponential rate. And here I show the evolution of bandwidth of these processors. And this line, I normalized it to start at this point, okay? So the units here don't mean anything. And you see that it has gone up at a nice rate, but at a slower rate, so there's an increasing gap. Okay, and this bandwidth affects, of course, everything. Access to memory, access to other nodes in a big network, or also access to caches, right? So you see there's a gap increasing, meaning that data movement has become relatively more expensive. And that gives you kind of the checklist how to get fast code. Oh, I forgot this one. Here, to make things worse, the variety of computers also has increased. Now that frequency scaling has come to an end, and you know we have to think, where do you get the performance? People get very creative in creating processors that are specific for certain kinds of computation. And here you see some examples, right? Some maybe more for the embedded domain. GPUs, of course, can do some things well, others not at all. Here are some very specific processors originally designed, I think, for software-defined radio and so forth. So meaning this parallelism and the bandwidth problem, it comes in different shapes and sizes. And if you optimize for one processor, it's very different than optimizing for another processor. So in summary, what do you need to do to get fast code? Clearly, you need a good algorithm, right? You don't want to do unnecessary ops. But then this red here, this is the checklist that I showed you with this evolution. You need to parallelize for cores. You need to vectorize the code. You need good locality so you don't access the memory so much. You want to reduce cache misses. And then you want to write, actually, this is a funny thing. You need to write the code in a certain style that the C compiler can process it well. Because some analyses are known to be very difficult on C code, for example. Good, and just to show you the insanity that sometimes that happens in the performance business when people really, really want to have fast code. Here I show you a Viterbi decoder. This is used in the LTE standard, right? 4G that you all have on your phones. It's actually the bottleneck. And let me show you a really fast Viterbi decoder. Non-vectorized, this is just C code. And this is how it looks. This is how fast code looks. Okay? So you see, who writes this kind of code? You write this kind of code if you are desperate, okay? If you really need speed, okay? And it's not just that this has been unrolled and that's it, right? It is the computation has been carefully arranged to have nice locality. So actually the variables are accessed in a way that they fit nicely at any given time into the 16 registers available. Good. You think this is looks tough? Well, of course, we just saw we need to vectorize code. Need to vectorize code, right? These 8x that you can get with vectorization. This is vectorized code, has fewer variables, the code becomes more compact, but then it looks like this. And you see this is explicit vectorization using intrinsics, right? And yeah, you see this is not necessarily easier to write, it's a lot faster. 8 to 10 times faster than the other code. So this is how fast code looks, okay? Good. Well, it's a crazy business, but you know, runtime is important, so people have to do it. Now, good, so what do people do? This is one approach. In fact, this is the common approach. So you have a lot of, not a lot, but quite a number of these guru programmers out there in the world, and they can do this kind of thing. They know very well how to get this close to the metal performance. And if it really matters, then you give the code to a person like this, and the person will produce this kind of code. However, there are not so many of these people, and so for most functions out there, you won't get fast code at all. Doesn't exist. So clearly there's some problem you can see, and this kind of screams for some automation, right? I mean, who wants to write this code, right? And clearly you want to have fast code as much as possible for as many functions as possible. That brings us to sort of the goal of this line of work that Daniele has embarked on, which is for one domain, and in this case it is linear algebra, to generate fast code automatically, right? The idea is, in essence, why does somebody need to implement a Kalman filter? A Kalman filter, as it was written, looks like a program. Why can we not just take this and from it generate fantastically fast code that may look as ugly as it gets? Who cares? It's generated. It's like assembly, right? And that just runs fast. And if you have another processor, you just generate different code for this process, right? So computer science is all about automation. Why not automate that? So that is the sort of the high-level idea. And the approach is really to take the math as an input. So we need mathematical DSLs, domain-specific languages, to somehow put this into a computer. And then we need to compile it into actual C code. But here's the interesting thing. We have seen that for some reason, or not for some reason, that the compiler, at least for many of these functions, has difficulties to optimize for vector instructions, to improve locality, and so forth. So we have to do this in our automated system somewhere, right? We want the red line, not the gray line. And the idea here is to do this sort of at a higher abstraction level, sort of at the math level, to kind of reshape things and perform these difficult tasks. And then only generate the C code when everything is neat, performance sense. And this is not impossible, because in this prior system that Martin has mentioned already, in Spiral, we have built such a thing for the domain of transforms and shown that this can be done, and it works quite well. Good. So where do you start? The good thing is we are researchers at the university, right? We don't need to build a product. So if you embark on a problem like this, it's good practice to start with the simplest case and see whether you can do something, and then if it goes well, you can move on to more difficult things. So what we started out with, or Daniele started out with, is what we call basic linear algebra. Basic, meaning the simplest kind of linear algebra. So now you may think, hey, linear algebra, I remember, there are fast libraries. There's BLAS and LAPACK, and there are these highly optimized libraries for scientific computing. So why do you care about linear algebra computations? Well, that's true. These libraries exist. And in fact, Intel maintains such a library for linear algebra computation. It's called MKL, and it's continuously developed. If you look, for example, at multiplying matrices, this is the peak performance of the processor, 16 flops per cycle, and the library achieves 91%. Okay, so this would be an example of a bad research project trying to improve this, right? Because there's nothing really to be gained. Okay, so there doesn't seem to be a problem here, right? However, you know, remember this Kalman filter, right? These matrices were size 13 by 13. So let's move a bit to the smaller sizes, then you see it doesn't look so great after all, okay? There may be room for improvement. And you know, if you go to people that use BLAS and you say, what about size 13 by 13? They will say, I don't care about 13 by 13. I'm solving linear systems, large-scale simulations. Because BLAS and LAPAC, their focus is really scientific computing and large-scale simulations. So this entire domain of smaller computations is really not in their target. Good. Are these small sizes important? Well, we have this Kalman filter. It turns out there are many such computations. Linear algebra is the universal math. It appears everywhere. So, I mean, here you see examples, optimization algorithms, you find it in machine learning, you find it in various control algorithms, in graphics, in signal processing. There's tons of small computations and many are linear algebra. For all those, you would like to have fast code. And very often, these have specific sizes, like the Kalman filter, size 13 by 13. In such a case, you would like to have ideally code that does that and exactly that, and not a general size library that is 10 times as big, because maybe you run it on an embedded processor and there's not infinite amount of space. And then BLAS, if you know this is the linear algebra standard for scientific computing, was specifically designed for those applications in scientific computing. The kind of linear algebra that appears in other domains, like control, for example, can be quite different. Okay? There are other kinds of matrices appearing, other structures, and other kinds of computations. And then again, in embedded systems, you really want to be as efficient as possible. Code size, performance is very important. Good, so small problem sizes have some importance. So now what is basic linear algebra? That's what we started with, the simplest. We said, okay, let's keep it simple. We only consider three kinds of objects, scalars, vectors, and matrices, and we support what linear algebra gives on. We can add, we can multiply by a scalar, we can multiply matrices or matrix and vector, and we can transpose. And then our block, basically in algebra combination, is something that looks like this. You can compose these into a single line of computation. For example, here a matrix is a scalar times a matrix transposed plus a scalar times a matrix, or here some more complicated expression. This is the input, and for this we would like to generate fast code and see how far can we get with this. Okay? Clearly these are building blocks for more complicated and more real world. So the Kalman filter will need pieces of this, but it's not sufficient for the Kalman filter by far. Good. So, and on top we said, let's work on specialized code. So the sizes of the operands are fixed, okay? Not a general purpose library. Good, so then the overall system is called LGen that Daniele implemented. And this is how it works. This is the system. The input is such a block plus information about the sizes. And the output is then code that looks a bit like this Viterbi decoder code, like this high performance code style, and it runs fast. And of course, we want to vectorize code, right? So we generate code that uses efficiently vector instructions, okay? And the goal is speed, So how does it work? And now I'll just sketch a little bit the inner working so you see kind of how something like this looks like. So the system operates in 3 stages, and in each stage we have a representation of the computation, and these are sort of the mathematical DSLs. Okay? In fact, the input is a DSL that comes straight from math. It's linear algebra. Okay? And this we call LL, linear algebra language. In essence, just linear algebra. Right? It's a language. Mathematicians have designed it. Works quite nicely. But then here we perform some optimizations on another kind of representation we call sigma LL. And that's a domain-specific language. It's math that we designed for the purpose of performing some optimizations on the code. Then some code is generated, some kind of intermediate representation for low-level optimization. And then finally we output the fast code. So roughly it looks like this. Up here, we decide on how the computation is kind of divided into pieces. You need to divide into pieces to get locality and reduce. Then here at this level, this looks something like this. We perform some loop optimizations in a mathematical way, and then we get this intermediate code, do some low-level optimizations, and in the end comes out function. Okay, so let me explain just a little bit how this looks like. Let's say, very super simple example. This is what we have. This is a matrix times vector plus vector, updating the vector. This is actually in BLAST, you find this as a BLAST2 function. Well, let's assume we want code for this, and let's assume it's a very tiny problem. So the matrix is 4 by 4, and the vectors have length 4. So it looks like this visually. Of course, that one would be not hard to implement by hand, obviously. Okay, so the first thing, we chunk up the computation. Now, everybody knows, if you have looked a bit in this domain, that you do blocking on these matrices and write the computation. However, here this is simple, but we need a general method because we have arbitrary blocks and we need to have a systematic way of blocking them, meaning dividing vectors and matrices into pieces. And the way we do this is that here, this is the tiling or blocking decision. So we assign to the entire equation two parameters, two blocking parameters. And then from this, we derive how the matrices and vector have to be blocked, okay? And the way this works, so from this tiling decision for the equation, we derive the tiling decision for the operands. So how does this work? In essence, we propagate these numbers up the abstract syntax tree. So first we distribute over the equal, and then you see the y gets the 2, 1, so has been divided. Okay, so we have already division. Here, the 2, 1 is assigned to this entire thing, so it's not yet on the operand, so we propagate further. By propagating further, we get a division like this. But there's still a degree of freedom how to divide this vertically and this horizontally. And we propagate further, and when there's a product, you get a degree of freedom. In case we chose k equal 2, now you have a decision, but you see that in this systematic way, a degree of freedom appeared k. And you can embrace this degree of freedom by saying, let's consider different k, generate the code, and pick the fastest. Right? Something called auto-tuning sometimes. Okay, so we have now formally, just with these parameters, chunked up the computation. Now we come to the next stage, and there more interesting things happen. And for this, we designed or used this formalism or language, if you want, Sigma LL. And a version of this we already have used back then and 10 years ago in Spiral quite successfully. And just to give you a glimpse, because this gets quite technical, what it does is it makes data accesses explicit. So in this formalism, data accesses become explicit objects that you can manipulate. And so in essence, the data accesses are gathers and scatters. Gather means you gather data from some vector or matrix, you gather a piece, and scatter means you take numbers and put them back into a vector or matrix. So, and these gathers and scatters are matrices. So look at this one, for example. It's a rectangular matrix, and if you multiply this to a vector of length 4, you get the first two elements, right? So you see it's a gather matrix. You can express things that in MATLAB are very common. For example, let's say you have this matrix in MATLAB, then you can extract this submatrix B like this, right? X ranges, and in our formalism, you can express this using two gather operators. It's completely equivalent, so you may say, oh, this is ugly, why don't you write it like this? We write it like this because the neat thing about this is these are matrices, matrix, matrix, matrix. Right? So you can, at any given time, you can actually verify, you can multiply together these matrices, algebra, and you get back the original matrix. So you still have the linear algebra available for operation. Since it's done by the computer anyway, who cares how it looks, right? So these gathers are these matrices, and the scatters are kind of the dual. If you have a matrix B and you want to put it into a larger matrix, you can also do this with MATLAB very easily, right? And in our formalism, these are scatter operators, right? And the scatters are also matrices, okay? Important, so the data accesses, that's the sort of the interesting thing here are represented as separate objects, but are matrices. So we are still solidly in the math domain. Okay, so how does it then look? So here's our computation that we have already divided into pieces. And in essence, this piece here, after division, looks a bit like this. So this is what's being computed after blocking it into pieces. So you take the first block of A and multiply to the first block of X and so forth. So it's composed like this. And that has better locality than doing the whole thing, because you operate on smaller pieces of data. And in our formalism, it looks like this, scatter, gather. And again, I want to point out, since we are in linear algebra, we can actually at any given time just multiply these all together and matrix, okay? Nice. And so this expression would correspond to this and this to this. And then you can use a summation operator. Again, this is a normal sum from math. Again, this is still all linear algebra. All matrices are normal summation. Write it like this. So you see, in essence, here you see the loops appearing. That would be. And yeah, and inside these blocks, you do the computation again on these smaller matrices, and that's a long sum expression. Scalars, which is also then expressed like this. So it gets complicated, but it's a useful formalism. So you can actually now factify this a little bit in this form. So you can rewrite these. These are matrices. They have identities. You can fuse them. You can simplify this to this, and this would pretty much be, if I write the code for this next to it in loops, you would already this one-to-one correspondence. Okay, so one thing we can do with this formalism is loop fusion, right? And so if you compute this, the naive way would be first you multiply A times X, you get a vector, and when you have this vector, you add this vector to Y. Okay. But that's bad, and if you implement this, typically you wouldn't do it. Instead, you would compute a piece of this, immediately add Y and update Y. So you have only one pass through the data, and that gives you better performance. So how do you do this formally? So here is the computation naive. First we multiply this, which is this, you get T, and then you add T to Y. And the fusion now does this, so it takes these two and outputs this, and that's the fused version. And in essence, what it does is this computation here, it inserts T here, and then you get this, and then you do some formal rewriting, because these scatters and scatters have identities, and you get this as an expression. So it's a loop fusion, and then you can generate code. Okay, and then it's pretty straightforward if you know the meaning of the operators to write a little compiler that converts this into some code, and we use some intermediate representation like in a normal compiler, so to do more low-level things, right? So clearly we want to do some loop unrolling and scalar replacement. In essence, what this does, it creates code of this ugly style that you have seen before, right? So you want this style, and we can do some low-level optimizations. Depending on the computation, there may be some common sub-expressions and so forth. Good. So far, so good. So we go from the math to the code. We still have to vectorize, though. And how do we vectorize? Now, compilers are not so bad at vectorization, and for many functions, compilers do a good job. In this domain, not so good, okay, and we will see. So how do we vectorize? So we vectorize in a mathematical way, right? We look again at the math, and we ask ourselves, if I want to generate code for vector instructions, how would I do this as a human? And you find very quickly out that what you would do is you look at the vector instruction and you see how long are the vectors. Let's say you look, you see, oh, this is the AVX instruction set, and the length of the vectors is 4. Okay, 4. So always 4 adds and mults can be done together. So then what you do is you would chunk up the computation in pieces that just map nicely. In essence, you want to have pieces of length 4. Okay, so here in this example, new is the vector length, let's say 4. And then what you would do is you divide it so that in essence you have pieces of this length, right? It's very intuitive. And then And you see, in essence, it's one step of tiling what we have done before. So if we vectorize, the first idea, quite simple, is do one level of this tiling that pieces up the computation like this. So you block like this, and then you can recursively add another level of blocking for the cache or so forth. So multi-level blocking. So let's say you impose this blocking size here, you get this computation, you get this, and now you see that in our formalism, this piece looks like this. So you see it's all nicely of length, vector length, and then this other part is adding 2 elements size new, so of course that maps very nicely to a vector instruction. Now, the interesting observation is in our formalism, we support addition, multiplication, multiplication by scalars, and transposition. Now you can ask yourself, using these 4 operators, how many such computations of size new do I have? So the basic pieces for vectorization. And the nice, so this we call a new block, right? Because it's a block, but it's all has vector, is vector length compatible, okay? Now the question is, how many of those are there? And it turns out, this is neat, there's finitely many, 18. And very easy to see, right? Addition, you can add like this. You have transposed vectors adding like this, and 2 matrices of size new by new. So this is addition. Scalar multiplication, you can multiply scalars to themselves or to a vector of things new or matrix of new by new and so forth. So these are all blocks where all the dimensions are either 1 or new. Finitely many. And what is now, and that was a design decision or a goal, strongly simplified, but still true. If you want to generate code for a vector architecture, you have to implement these new blocks once, and then the system can generate vector code for it. Okay, because it's finitely many things you have to do, and there is no creativity. You just have to implement them in the vector instruction set, insert into the system, and you can generate vector code. And this was an important goal because we want to be able to port from old processors to new processors with new vector architectures. So if suddenly Intel comes out with AVX3, right, which has a longer vector length and whatever, then it should be sitting down for 2 days doing some horrendous coding work and then be done. And then the whole generator can produce code for this new architecture. That was the goal. We want to port forward. Of course, in reality, you not only need to implement these, you also need to implement some gather and scatter operators, right? Because port uneven vectorization, like length 3, then is loaded into a vector of length 4. You do the computation and you gather out the result. Okay, so in fact that was also important. For small sizes you want to handle the ugly leftovers, right, which is not divisible by 4. Good, so let's look at some performance results. Before that, so the degree of freedom here is tiling, right? This K I showed before, the way you chunk it up, there's some degree of freedom. You can do search over it. We do here so far a simple search and a little bit of a model. So it's not terribly interesting. So let's look at some experiments. So here's a processor that we worked with. Here you see all the details. What are our comparisons? These are the serious competitors. These are performance libraries maintained by Intel. They have these guru programmers. They know very well how to optimize code. They do write an assembly if it really needs to be. And in fact, they do write separate assembly for all their processors. I know for FFT there are 5 versions. Titanium, there is SSE, there is AVX, there's AVX 512, and then there is Atom, all written in assembly. So there you see how crazy it can get. So these are serious competitors. This is fast code. And there are some prior approaches. LGen uses C++ templates to create fast code. So it's an open source project. And BTO from Jeremy Sick's group, Build to Order BLAS, is another attempt to sort of generate code. Good, so I show you plots like this, performance plots. Here there will always be some size that increases, and on the y-axis, flops per cycle. The peak performance of this processor is 8. Okay, we don't reach 8, so the plots will always end at 6, which You also don't reach, okay? But anyway, so we end at 6, and then it looks something like this. These whiskers are quartile information, and the measurement, typically it's, okay? So it looks like this. So this would be 50% of the peak performance. So first, something very simple, matrix times vector. And surprisingly, you can get a speed up. These are matrices of size n by 4. So in essence, like this matrices. And here you see all the competing libraries. So you see we are quite a bit faster. In this case, Eigen is quite good. And I want to point your attention to these ones. This here is naive code that you would write. I mean, you could all write this code, right? It's just a bunch of loops, right? Multiplying matrix and vector. This is this code, the standard loop code. And this is the same code where the size information, so in this case 4, has been hard-coded into it. Okay, so this is what I call the straightforward code, the gray line from before. So you see, again, we see this big difference between the, down here, the straightforward code and the best code. And you see we compare well against the libraries. You see if I flip and have matrices like this, somehow everybody gets better. This is a bit of higher importance, this kind of shape for higher level functions. So you see where the optimization effort goes into. It's very clear they spend more effort here. Our generator is completely blind to these things, has no preference. It just produces code. So you also see we don't always win, right, against the others, right? But it's automatically produced. But here's something that is close to a BLAST3 function, dgem, multiplying two matrices in this particular form. Again, we just chose here some shape, and you see big gain, and here is again less, again because this is more important for these kind of functions that you find in this library called LAPEC, and in particular in scientific computing matter a lot, right? But there's no reason why in other domains not this shape should be. And here's some function that we just invented. It's a more complicated computation, so no library out there supports this natively, so you have to piece together library calls. In MKL, you need to call 2 times 2 libraries to do this, two library calls, and again, you see good performance. So you see you really gain something, right? And it's not negligible. And here's some things, very tiny computations, really tiny, like multiply 2 matrices of size 7 by 7 using 4-way vector instructions. That bit of code looks already quite nasty, and it's nice to be able to produce it and get some gains. Okay, really tiny computations. But tiny doesn't mean that you don't want it to be fast. Okay. Good, embedded processors works also well. This is Anthem and ARM, right? Both in the embedded domain. These are in-order processors. Also here we get gains. Good. Let me skip this. Some little optimization using abstract domains to find aligned loads, but that's a detail. So, great, we can do these very basic computations, but remember the Kalman filter is far away from this. So how do we get there? So we did the blocks. That was step number 1, and we published it. Step number 2, to go towards the Kalman filter, you really need support for structured matrices. Okay? And structured means symmetric, triangular, they just appear, right? If you want to do Cholesky factorization, first it operates on symmetric matrices, second it produces triangular matrices. You want to support them efficiently, it requires only half the work. So that was the second step and was published this year. After we had this, we could start to attack higher level functions, and meaning like Cholesky factorization is a higher level function, and there we collaborate with these 2 people, and they have this super nice tool. Sorry, I'm ahead of myself. This is what we are currently doing, and then the Kalman filter, which I put, is not yet. We don't have this yet, okay? But this is the 3rd step. Once we have this, then it's not so far anymore to go there. So these people, Paolo Biantinesi and Diego Fabregat, they have this very nice synthesis tool. It's real program synthesis that produces algorithms for higher level linear algebra functions. And I don't want to explain it in detail, but if you like synthesis, I really invite you to look at this. Unfortunately, they come from the scientific computing domain, and I think they really should have published this where other program synthesis work is published. And what they do is they take a mathematical description of Cholesky factorization, like S equals LL transpose, and then they have a system that produces an algorithm, that synthesizes an algorithm. by in essence chunking up the computation, getting the sub-expression you need, then automatically generating a loop invariant, and from the loop invariant they generate this code. And you see as high-level code, it chunks up things, and then it has these blocks, right? So then what we did is we work now on, in essence, taking this output and feeding it into our system, in essence here generating the blocks, and these are all gathers and scatters operation, and then optimizing the whole thing and hopefully getting code. And the nice thing, it works already. This is the latest, greatest, 2 weeks old. This is solving a triangular continuous time Sylvester equation. Don't ask me, it's used in control theory. It finds x given the other three matrices. So it's a non-trivial thing. And you see here, MKL actually has it. So you see we get also here 2x over MKL. Here we were a bit too excited first, but even if you divide this by 2, I just found this bug yesterday. Factor of 2, too good. It's in reality here still 2x. This is a Cholesky decomposition. We are equal. And this is a triangular inverse. What is really nice, the tool that they have can generate many algorithms, and most have never been implemented, because it takes a bit of an effort. And now that we hook it up with our generator, all of these can be actually brought to life. We can generate code for all of them and pick the best, because they also didn't know which one was best, right? The differences here are not so big, but for larger sizes get a bit bigger. Good. So that's the story so far. So I told you that the vision or the goal is you take linear algebra from a book, no matter whether it's control or machine learning, whatever, and it would be great to just push a button and you get fantastically fast code, highly specialized to your needs. Okay, that's the goal. And we try to achieve this with LGen, that in essence takes the math, produces fast code. It uses some levels of DSLs. To achieve this, performs optimization at different levels, and it already produces some good results, including for some higher level functions. So you see that in my list that I showed before, step 1 to 4, we are at step 3 right now. So if I come back to the Kalman filter, this is something Daniel is currently working, and I think he's almost there, right? Because it's all blocks, and here's some Cholesky things, right? So I think a few more weeks, and he has it, meaning that we can take this, plug in the ugly number 13, and get nicely vectorized code automatically. And yeah, like this, there's more information on this.
Yeah. So you said that BLAS is somehow optimized for larger matrices.
Yeah.
So you're faster for small ones. Where do these sort of curves meet? Where do they get faster?
It depends on the BLAS implementation, right? I mean, there are different BLAS implementations. One is from MKL. There's a project called Atlas, and there are other groups that have implemented BLAS. It's hard to say. It depends a bit on the BLAS function. But let's say, to say something, once the working set doesn't fit into level 1 or latest level 2 cache, we start losing. Because then parallelization matters, and the truth is we didn't do some optimizations that you need once you get into these regimes of lower bandwidth outside of cache. So we could expand the generator to include these optimizations. They're published, it's clear what you need to do, but that's not currently the focus, right? So that's why we focus on the smaller things. But around that area, we have the crossover.
Okay, Jim. So, Markus?
Yeah. There's sort of two things that are interesting. One is that you're doing fixed size matrices that you know in advance, and so you don't have the overhead of doing the calculations at runtime. The other one is that you're optimizing across an expression, not just doing sort of BLAS style function calls on each operator. So how much does each one contribute to the results that you get?
How much does each? So it's true that MKL, because the libraries are, or IPP, all libraries are general size, there's a little bit of an overhead, which is not very much compared to the overall computation. The computation like n squared and cube, and the overhead is linear, let's say. But for small sizes, there is an effect. That's true, maybe 10-20%, I would say. Then the issue with, for some expressions, you need more library calls. That also has an effect, but it's also not very big. So we have looked a little bit into this, and it doesn't explain all our gains. And it's clear that because there are things like, for very small sizes, leftover sizes are not handled efficiently because asymptotically they don't matter, for example. And then the code style, we can of course have a degree of freedom to employ really a very high-performant code style for the small sizes. Whereas if you optimize for larger sizes, the kernels inside the loops matter more, and the kind of code you would write is a little bit different, right? Well, they clearly could do it, right? Sort of these overhead things account only for a piece, maybe a third of the overall speed up. And what is also really important to understand is the specialization to size is not a bug, it can be a feature, right? Because if you only need one size, you can gain a bit additional performance by specializing to this, and clearly we gain there as well.
Next question. Yeah.
So in Flux, do you also optimize the leftovers of matrices?
Yeah, exactly.
For instance, if you have a matrix of size 7 for whatever, and mu is equal to 4,
Yeah.
so do you treat the 3 rows left over as a matrix, and then you get an extra vector scalar product for 3, for instance?
So we can do both things. You can do two things. You can take the leftovers and leave them in normal C code unvectorized. Or you vectorize this as well by embedding, for example, if you have a 3 by 3 matrix left over, you can embed it into a 4 by 4 matrix, which you can load into vector variables, and then you do some optimization or some operations where the last slot is kind of 0, and at the end you have to store back. So we do exactly this is what we do also. And then you can see which one is better. For small sizes, the latter one is better. And that exactly leads to a kind of code that is already quite difficult to write by hand properly, right? Because these loading 3 elements into a piece of a vector, and then, things get tricky. And the code looks quite ugly also.
Yeah. How do you do inversion of matrices?
How do we do inversion? Right now, we do inversion only of triangular matrices, okay, which is pretty straightforward. A complete general matrix inversion algorithms we don't have yet. And there are several reasons. Maybe we could not do it right now. Would be a bit more work. But as our linear algebra friends, because these people, Paolo, Vientiniesi, and Diego, they are linear algebra experts. They say in linear algebra you never invert a matrix. They say this is a ground rule in linear algebra. You never do this. You do a new factorization, you solve a linear system, but you never explicitly invert. Where the never is probably not a 100% statement, right? But people in linear algebra, they don't do this because it's unstable. It's inferior to implicitly doing things like factoring and solving linear systems. So typically what you do is with matrices, you factor them LU or Koleski, and then you work with the triangles, and there you may invert. So it's not so important.
Yeah.
When you're actually doing the optimization, do you use much information about the actual target architecture, or do you just rely on this parameter search you do to sort of generate the best code you can?
So right now, you saw we use the length of the vector architecture, and of course, we have to implement those new blocks, which takes the entire vector architecture into account, and associated scalars and gathers. So in that sense, the actual instruction in the vector architecture are being used. So we use that. Beyond that, the system would work without any other information. But Daniele has a tiny little model, which is also from the literature. There's work on this at the register level. How should you block these operations? And there it's useful to know the number of registers. It's also known how to block so that you optimally for the level 1 cache. So also there you could use a model, but I don't think we are doing it.
Do your results here, how long did you spend actually tuning the parameters?
The parameter tuning is very little here. So this was, he uses mostly this simple model I explained, and in all these experiments we generated only 10 random variants. It's an extremely stupid search, 10 random variants and pick the best. So it's not that we because I always like to de-emphasize the parameter tuning because it's a bit unelegant, and I think the nice part of the work is all the rigorous parts of it, like rigorously blocking, rigorously breaking it into new blocks, rigorously doing the loop fusion, right? That's all formal and clean, right? And the tuning should work without the tuning quite well.
So I have one last question. So this Kalman filters, from what I know, it's like special kinds of Bayesian filters, and many people in robotics, for instance, they're using particle filters, approximations like this, and you can just, you don't even have to write them as matrices there, you just write them as a Bayesian network, basically, as a high-level language. So what are your thoughts on, like, let's say particle filters, other kinds of filters?
I haven't looked at particle filters. I know they are hip. They came up, like, I think about 10 years ago, and signal back then I was still around by signal processing people. I haven't looked at this, right, because I wanted to pick first something that is solidly within linear algebra, and this is big, so it has exactly the kind of functions that, you know, blocks and Koleski that we can handle, and we wanted to have something in the domain with matrices and vectors, right? Because anything beyond would require additional work. So for Daniele, that would not make him smile. Right now, right? But I think it's something when this is done, one can look at domains like this. I must say, I didn't look too closely at particle filters. Okay, yeah, I don't know enough about this. One would need to look.
All right, good. So let's thank Markus again.